Most parts of it are familiar, and specifically the Q1 and the Q3, because you can pull that right out of the calculator. Like when you do stat calc 1, there's a Q1 and there's a Q3. So regardless of what those actually mean, you could actually just say, well, Q1 according to the calculator is this, Q3 according to the calculator is that. The IQR is what? Interquartile range. And we compute that by doing what?
Third quarter minus the first.
Exactamundo. I can't write this right now. Q3 minus Q1. Okay, so you do all that. You can follow the formula. The hard brackets tell us that this is a closed interval. So whatever falls in this interval would be considered not an outlier. Whatever falls outside would be. All right, so the boundaries are not outliers. Whatever's beyond the boundaries would be. All right, so you can do all that stuff to these numbers by hand or in your calculator, but let me show you something else. All right, so stat edit, type in your numbers. Just a refresher, something you should already know because you probably have experienced this the hard way. When you want to clear out a column of data, up to the column heading, hit clear, not delete, and then either down or enter, and it'll wipe out the whole column without deleting the column itself. All right, because you run out of L's very quickly if you do that. By the way, if you accidentally delete an entire column, just go to the next column and hit second delete. Right above delete, it says INS for insert, and then name it what it was before you deleted it. All right, it was L1, which is second one. So hit enter and it'll bring it right back. All right, so if it happens, let me know, and you don't remember how to take care of it, let me know and I'll help you. All right, so I'm going to type these values in: 2, 4, 5, 6, 7, 8, 9, 10, and 42. All right, just based on visual inspection, it seems as though that 42 is probably going to be the only candidate to be an outlier. All right, but we want to justify it mathematically. All right, so what you can do is, and this is not the trick, you could do the stat calc 1, have it point to L1, so your list is L1, it's not a frequency table, so right to calculate. Scroll down and get your quartile values, Q1, Q3, 4.5, 9.5, IQR would be 5. All right, and then you could do the computations. All right, now I wrote a program for this, so I wouldn't have to do this every single time, but at least for one time you might as well get the experience. So 4.5 minus 1.5 times 5, and then 4.5, not 4.5, sorry, 9.5. Plus 1.5 times 5. All right. So 1.5 of 5, taking 2.5, tacking it onto the 5, so 7.5. So you're taking 7.5 away from 4.5, so you're looking at -3. On the low end, on the high end, you're looking at, so you're adding 7.5, so you're looking at 17? Yeah. Almost at 16. All right, so therefore 42 is an outlier. Okay, so cool, but again, not the trick. If you just need to determine what the outliers are, or determine, a question asks you, determine whether this number is an outlier, you don't need to do any of this. All right, you do have to put the data in, right? Otherwise the calculator is not going to know what the heck you're talking about. just like yesterday, second y equals, go to your plot. I just kind of live out of plot 1 and manipulate it as necessary. So enter on plot 1, turn it on. Oh, and by the way, this is something I neglected to mention yesterday. I think I obviously did it, but I don't remember doing it. I mean, actually, maybe I didn't. Maybe somebody else had to do it. But if you're typing stuff in like regular function mode, you want to create a graph, and you have a plot on with no data in, you'll get that error dim mismatch. Right? That happens from time to time. That's the stat plot interfering with the other kind of plots that you want to create. So if you're in calculus and you want to create a graph, make sure you clear out the entire top row here of plots. So hit enter to turn off everything. All right, so that you don't get that annoying error message when you try to do something calculus related. All right, but when you're in here, you want to turn it on. So second y equals plot 1, turn it on. We're gonna kind of cut to the chase here. I haven't even shown you how to graph any of these things by hand, but we're gonna jump right to the modified box plot. All right, so if you have no idea what a box plot is, then how you would modify one would definitely escape you, but you have seen box plots before, also known as box and whisker plots, but that sounds stupid, so I just call it box plot. All right, so X list is L1, my frequency values are 1 because each value in L1 occurs once. The mark, that's optional. That's just how you want your outliers to be represented on the graph, if they exist. Zoom stat, so that's zoom 9, and I have that other stuff in because even though I was in that window that said I have 2 graphs, I, for whatever reason, opted not to turn either of them off. By the way, you should know this. If you don't, here's some knowledge for you. You don't have to clear out equations. You could just hit enter on the equal sign to turn them off. All right, then they won't appear. All right, so if you need your equations for calculus, you don't want to delete them, just turn them off so that they don't interfere with your statistical graph. All right, now when I hit trace, any loose point, anything that's not connected to the main box plot is going to be an outlier. All right, so these are all fine. There's my outlier. All right, so thinking in terms of the AP exam or even a unit test, multiple choice question. You don't have to show any work. It says determine whether whatever is an outlier. Put the data in, create a modified box plot, take a look at the picture, and then call it a day. All right, no need to do any of this stuff. All right, so nice little pieces of information for you. Also, something to bear in mind. In AP Calculus, there's a calculator part of the AP exam and then a non-calculator part of the AP exam. So you can't use a calculator at all. In AP Stat, you can use the calculator the whole time. All right, so I mean, sometimes you have to write like a lot, explanations, things like that. Calculator's not going to help you, but you have the calculator available the whole time. So you're going to be in pretty good shape when it comes to that. So these calculator tricks, they're always going to be available to you. It's not like what I would say in AP. Well, here's a calculator trick, unless you're on the non-calculator part of the exam, in which case it's going to do you no good. All right. Now, when it comes to frequency tables, it's all the same, except you're applying frequencies instead of just looking at it as a single column. So stat edit, clear out my column, 1, 2, 3, 4, 5, 10, 3, 1, 8, 5. All right. So when I do my stat calc 1, it should be pretty obvious, stat calc 1. You just have to know to put L2 in as your frequency list, all right? So depending on the type of data you're working with, this is good. You're gonna have to be flexible with your frequency list. You're either gonna leave it blank or you're gonna put L2 in there. It's gonna change from problem to problem, all right? Calculate. From that, you can pull out your mean and your median. So your X bar for now, until we get some context, we'll just call it X bar. All right, so 2.815 approximately. And I'll go at well, I was going to say the sample standard deviation, but it asks for median, not standard deviation. So the median is 3. Now, in the case of the next example, it's asking us for an estimate of the mean and median. All right, so that one's a little bit easier to conceptualize because you already know how to handle this. It looks like it would be more challenging. Like, how do I come up with an estimate? What do I do? Pick random values in the interval of 10 to 19 and so on. What you use is the class midpoint. All right, so the average of the high and low value for each interval. So here, I would take the average of 10 and 19, which is what? 14 and a half. All right, and so then 24 and a half, 34 and a half, 44 and a half. So that's the only adjustment. So it's not a problem at all because we already know how to do this now. Because this is what we're going to use as our set of X values against the F values that were already given. All right, so we're just going to type those in. There is if you have incremental values that you want to type in as a list. Now here there's only 5 values, so it's not terrible to just type them in. But if you have values that increase incrementally and you want to come up with a rule that allows you to do that, this is killing me. I got to get that light bulb changed. I'm just debating whether or not it's worth it to show it to you now. You're familiar with sequences, right? Okay, so it's probably worth it. So what you could do is hit enter on L1. Obviously, again, it's not worth it for this problem, but if you had to type in the numbers 1 to 100, you would want to use this technique, all right? So let me just kind of, as a brief aside, show you that. Sequence feature. All right, so it's second, stat, ops, 5. All right, but first you're going to hit enter on L1. All right, so this is a rule for L1. All right, anytime you want to make a rule for an entire column, you got to do it on the column heading. All right, so that'll bring the blinking cursor to the bottom of the screen. So now I hit second, stat, ops, 5. It brings up the sequence function. All right, so expression. We're going to call that X with a variable X. All right, so that would be like if you're in, I don't know if you did it in pre-calc, but definitely Algebra 2 honors if you took that, but a little bit in Algebra 2. Now it's in Algebra 1. If you ever saw A sub n equals n, where n is greater than or equal to 1. All right, that would be saying my first entry of the sequence would be 1, followed by 2, followed by 3, followed by 4, and so on. All right, so this allows you to go a little bit further, and that's what I typed in, by the way. My expression, I'm using X, but you always have to tell the calculator that whatever you're typing in as a letter is not really just some arbitrary placeholder, that it's taking the place of a variable, so you got to tell it what the variable is. All right, so because you could actually store numerical values in for any one of the letters that are available on the calculator.
So when you do the sequence, you can store that in L1?
You could store it in L1, yeah. So I'm going to start this sequence at 14.5. I'm going to end it at 54.5. Right. And my step is 10 because they're separated by units of 10. And then it'll pop it all in one shot. Again, not necessary, obviously, to type in 5 small numbers, but imagine a case where you had to go from 14.5 to like 1,224.5 by tens. You know, like it would be problematic, obviously. And you know, I look at the stat editor here as Excel light. You know, a lot of the features that you may have experienced if you've ever used Excel, they're kind of in here, but in a different sort of way. All right. So if you're familiar with spreadsheets, then you definitely already know how to use this. It's just a matter of learning the language. All right. So 51, 13, 22, 4, and 92. All right. So then I do my stat, calc, 1, L1, L2, and then I can calculate, and I have what I need. All right. Again, just estimates. All right, so again, just so I have complete notes here, it's going to be when you use second stat ops 5, the sequence function, it's the expression, the variable, start, end, and step. Those are the relevant ones. So we started, or we had x and x, 14 and a half, 54 and a half, and we went by tens. Again, pretty good feature to become familiar with moving forward. If you're in BC Calc, who's in BC Calc? Okay, so BC Calc, you're gonna be spending like the back end of second semester on infinite series, which is related to this material. So, I mean, this is like the most basic element of it, but it'll give you a little bit of a segue into it. All right, so standard deviation, there's lots of information there, and you can read it all thoroughly, but and I recommend you do and take notes on it. But I'll give you the overall gist of it at this point. Really, standard deviation is talking about the idea that data sets have some sort of spread associated with them, right? So unless all the values in the data set are identical, in which case the standard deviation would be equal to what? Zero. No spread, standard deviation 0. All right. So what we're doing is standardizing the overall distances that any element of the data set has from the mean. All right. And then when you look at something like linear correlation and regression, if you remember that, the line of best fit, that's just standard deviation in two variables. All right. So you're looking at a standard deviation from the perspective of x, and then the standard deviation from the perspective of y. But then we put it all together. Right, that's why they actually, another name for it is called the least squares line, because you're minimizing the square distances away from the trend line, but that square distance is the hypotenuse of the right triangle. Right, so if I were to have a set of points and a line segment going through it, you would be looking at a straight line distance. You'd have a horizontal distance associated with that, and I would go right to the line, for example, like this. We'd have these two legs of the right triangle. What I want to do is minimize this. All right, if I could minimize that hypotenuse, then necessarily I'll be minimizing the legs also. All right, so it has a little bit of a calculus flavor to it, because you talk about extrema, maximum values, minimum values, right? So we make that as small as possible, all right? But what these two represent are deviations from an average value, right? So that's what we're trying to do. We're trying to find how much deviation overall a data set shows from its average. All right, if all the data points are exactly the same, then there is no deviation whatsoever, so standard deviation is equal to 0. If it's widely spread out, then you would expect the standard deviation to be somewhat large. All right, but standard deviation is a comparative value. All right, so if I tell you that the standard deviation of a data set is 2, you'd say, okay, there's some spread. But if I follow that up by saying, how much spread is there? You might say there's 2 of spread. Be like, all right, very good. And then I tell you, okay, here's another data set where the standard deviation is equal to 6. Then I ask you, which data set is more spread out? Now we're talking, all right? Because now you can tell me, okay, the one with the standard deviation of 6 is more spread out than the one with the 2, all right? Because it's a comparative value, we can make a determination of how spread out data are, but it doesn't really tell us too much until we start comparing it to other data sets, all right?
Isn't it also dependent on like the sample size and like what, like the thing it says in here about weight and like money?
Exactly. So depending on the situation, if you have, I mean, you could collect data on any number of topics, but the more you include of a particular item, the tighter your standard deviation becomes because of what they call the law of large numbers. So in probability, you can really kind of flesh that out pretty easily, because the classic example is if you flip a coin once, you might walk away and say, okay, probability getting heads is equal to 0 because I got a tails. So you're never getting the heads. All right, flip it a second time, you get a tails again. Oh, yeah, see, I was right. You know, flip it 10 times, 9 out of 10 times you got tails. Is the probability getting tails 9 out of 10? No, or 0.9. But if you increase the number of trials, you get up to 1,000, 10,000, a million, whatever, you're going to get closer and closer to that 50% mark. The same thing is true with standard deviation. As you increase the sample size, you're going to get closer and closer to the true standard deviation. And so then you start getting into something called the central limit theorem, which is the subject of something further down the line. But the comparisons come from the idea that we can take, and this is an overall theme of the course, we can take information about samples, small samples, and use them to project out to the large population. I can draw conclusions about entire populations by knowing characteristics of small samples as long as I know that that sample is representative of the population. All right, so if the sample embodies the same characteristics of the population, then I'm able to make those conclusions. I can say what's true for the little guy is true for the big guy. All right, so it's like a projector. I look at it that way. Yeah, I think it's in one of your later packets. I put a little graphic in there. But if you have like a projector with slides, you know, you look at the little slide and it's like got the little tiny picture of a tree on it with little tiny kid playing in the playground, and it's like adorable. And then you put it on, you know, in front of the projector and it blows up on the big screen and you're like, whoa, that tree is dead and that kid is miserable. You know, like, because you could see all of the details, all right? So what happens is you're going to lose something in the projection. But what we want to make a determination about is whether we're maintaining enough of the integrity of the conclusions about the small sample so that we could use that to drive inferences about the larger population, all right? Because, you know, it's the kind of thing where, you know, like if you've ever, let me ask you this. Have you ever been in a class where the teacher still uses those overhead projectors with the plastic slides and then they write on them?
Yes, chemistry, 2 years ago.
Yeah, they still use them.
Wait, 2 years? Here?
Yeah, Mr. Arena.
So does
Wow.
Nova. I don't know why they use them.
I honestly, I thought you were going to be like, yeah, I vaguely remember in second grade, like a bunch of years ago. No, okay, cool. They're still rocking that. That's
They do
awesome.
this cool thing where they have, I think it was for some unit about like molecules, but they put this tray on it that has all these like little beads in it.
You get to watch them.
Oh, okay.
No, but
they also write
Oh,
on
but
it.
they also read it. Okay. So, but you look at their little slides that they write on. It looks beautiful, right? But then they put it up on there, then you could see like the little piece of hair and the little like specks of dust and stuff like that. You know, that's really what it is. You lose some of the quality of the inference from the small to the large, but if you can maintain the integrity of it, the overall structure of it, then you will have drawn conclusions about, you know, the entire population. And so standard deviation drives all of that. All right? It's the, well, I'll just tell you, you don't have statistics without the concept of standard deviation, because you could find out what the central value is for a data set, but without knowing how spread out the data are, what's the point? I could tell you, for example, that on the last unit test, my students got an 80 average. All right? That's actually not too bad. 80 average. All right? With a standard deviation of 0. So everybody got an 80. So you're a student in that class. Are you happy? Depends, right? Depends on the situation. Now, like I can add context to that, and I'll say that they're second semester seniors, and this was the end of the line, and they weren't overly concerned at that point. So then maybe add that little context in there, and it's like, oh, okay, cool, yeah, maybe 80's all right. But that didn't actually happen. What happened was the mean was 80 with a standard deviation of 10. All right? So the usual unusual rule, which we'll talk about more, tells us that if you're within 2 standard deviations of the mean, you're not unusual. You're in the usual territory. All right? And this is true for anything. If anything, any data set that can be defined as a normal distribution, if you look at it that way, where if you have the standard deviation and determine what the boundaries are for 2 standard deviations below the mean and 2 above the mean, then you have determined what the usual range is. Anything outside of that would be unusual, right? So in my case of mean of 80, standard deviation of 10, what's the low bound of usual? If I'm going 2 standard deviations below 80. 60. All right, what's the high end? 100. So what does that mean? So contextualize that.
You can't pass and be usual, and you also can't get higher than the usual.
So 60 is the low end of usual, and 100 is the high end of usual. So anything beyond those numbers would be unusual. So if we call, 65 they say is the passing mark, but we'll go with 60 just to keep the numbers convenient. So if you contextualize that, it's basically saying that it would be unusual to fail, and it would be unusual to get a score above 100. Does that sound reasonable? Yeah. All right, so that spread makes sense. Now, if I tell you that the mean is 80 and the standard deviation is 1. Now we're talking 78 to 82. Unusual to get below 78. All right. Cool, I guess. Unusual to get over an 82. Well, I don't want it to be unusual to get an A or even a B plus. Right? So standard deviation makes all the difference in that case, how spread out the data are. All right, so that's the motivation for learning this. You know, that's in an academic sense, but you can really just kind of expand that out to anything. All right, you think about athletes, you can think about earnings in a business environment. My classic example is the waiting time at an airport to get through security. That's my favorite one. Because if I tell you that, and like I just got TSA pre-check approved, so things are different now in the CAN household. But before that, it was like, okay, we're going to JFK. It could take 5 minutes to get through security, or it could take about an hour. I don't know which one it's going to be. You know, so if I tell you you have a choice, you could have a mean of 5 minutes with a standard deviation of 5 minutes, So anywhere between no wait and 10 minutes, or if I tell you a mean of, let's say, 7 minutes with a standard deviation of 20 minutes. Bigger swing, I mean, still maybe not waiting at all. Negative time. I don't know what that would even mean. Like walking backwards, I guess.
They give you money to walk through.
Yeah, something like that. Or you're already on the plane and you have to like leave somehow. Or you could be waiting upward of 27 minutes. I mean, these are low numbers, but you get the idea. You know, so waiting times are a good application of it. And you can really kind of consider that the next time you're sitting at a drive-through. Because I think it's stuff like that too. Some places are better than others. Waiting time is more consistent at Dunkin' Donuts drive-through than it is at Starbucks. Fun fact of the day. So, student in my college class did a study on that. So it's not like world conclusive, but it's like lower Westchester County conclusive. So something for you. All right, so when using standard deviation, keep in mind the following properties. It's only used to measure spread or dispersion, fun word. Standard deviation is never negative because it's a distance, right? A distance could be negative in general, but it's implying direction. All right, so if I tell you the standard deviation is -2, I'm just telling you that it's 2 the other way. But if I need to go in both directions, it doesn't matter if it's positive or negative. In fact, we could think of it as an absolute value. It's very sensitive to outliers. All right, this is one of those things that, man, I would just love it if right now I say it, it's ingrained in your brains, and you never forget it, ever. And so when it comes up on a test as one of those Roman numeral questions, which of the following is true? Roman numeral 1 only, Roman numeral 1 and 2, 1 and 3, none of them, all of them, you know, that kind of thing. You'd look at that and say, yeah, of course it's sensitive to outliers. But let's say you're in that moment and you completely forget. What's something that you could do?
Simple set of data and throw something that's like much higher. or
You're
much lower.
damn right. Absolutely. Yeah, make up a set of data and throw in something that you know in your heart is an outlier and see what's going on. All right, you'll see that that's going to destroy your standard deviation. All right, so for data sets with approximately the same mean, the greater the spread, the greater the standard deviation. Again, something, memorize it. It'd be great if you're one of those folks, but you could also invent that rule on the fly if you need. This was, we talked about it before, but I think as you think about it, it's just common sense. Right? Units of measure of the standard deviation are the same as the original data. All right, so if you're talking about number of people in a classroom, then the standard deviation, if it's 2, it's 2 people. All right.